So this video sort of follows on from the two-way analysis of variance with post hoc testing. I want to just go through how to do the BoxCox transformation. So if we go back to the test for equal variances here, now you'll have to sort of you have to sort of follow me for a minute here. Imagine if this p-value here had come out to be just below 0.05. Remember, this is Levene's test. This comes right at the start of the analysis. I mean, the first thing I would always do with any data analysis is have an eyeball of the data. So I'd always want to build an interval plot, a scatter plot, or a box plot, or whatever, just so I can get an idea of what the data relationships, associations, differences looks like. Our eyes are good at spotting any patterns. So for this plot here, like I said in the previous video, imagine if one of these error bars here was huge and it was sort of straddling right across the graph there, and the error was going right across all of these other error terms here. That would be telling me, that would be ringing alarm bells for me straight away, telling me that there is not equality of variances. Remember, the variance is just an expression of the error, the spread about the mean. And for an analysis of variance, general linear model to work, we know one of the really important, utterly non-negotiable assumptions of that analysis is that there is equality of the variances, or no significant difference in those variances. So we use Levene's test to check for that. And in the video, in the previous video, the doing a two-way ANOVA video, we could see there was no problem there. So let's imagine that there was a problem. Let's imagine that was just a little tinsy bit below 0.05. And that means that we reject the null hypothesis that there's no significant difference in the variances. That puts the brakes on any further analysis until we can get that Levene's p-value up. Now, built into the ANOVA, the general linear model menu, hidden in the options, is the option to do a BoxCox transformation. This is a fantastic transformation which brings in a whole range of power transformations, and it means you don't then have to fiddle around going up into the calculator and think, right, well, I'll try taking the log to the base 10, I'll try taking a natural log, I'll try square rooting the data, I'll take the inverse, I'll do an x minus 1 or x plus 1 or whatever, and you just sit there for hours faffing around trying different transforms. If the data is going to be transformable, then a BoxCox will hopefully find it for you. If the BoxCox transformation doesn't work, then that's a good sign that you should probably give up on a data transformation, or give up on any of the common data transformations anyway. If your departure from the assumptions of your analysis is either non-equal variances, of course you could be finding that you've got a small sample size and you get your residuals at the end, and you see that your residuals are markedly non-normally distributed. BoxCox will help out there. It's quite complicated, the BoxCox transformation. I did a whole lecture on data transformation in research and analytical skills, and you should have access to that lecture. It would pay, if you need to do a transform on your data, it would pay to go back over that first of all and see what's going on. Now, the parameter in the BoxCox transformation is lambda here, and as you'll recall from the lecture in research and analytical skills, different values of lambda are the equivalent to different common transforms. So a lambda value of 0 is a natural log transform. A lambda value of 0.5 is a square root transform. You could put in a specific value of lambda. Really, what we're in the business of, though, is we don't know what transform to do. So we're telling Minitab, just try a whole load of transforms with loads of different values of lambda, and then find the best value of lambda that brings your data closer to normality. And the thing with making your data more normal is that usually has a stabilizing effect on the variances. I've seen lots of occasions where a BoxCox transformation doesn't work. If we've got a huge departure from normality, or a huge heteroskedasticity, what a marvelous word that is. Heteroskedasticity meaning variable scatter, in other words, non-equal variances. If that's a really marked effect or a really marked non-normality, BoxCox ain't going to work. But choosing an optimal lambda BoxCox will help. Is about the best you can do if you're not sure what transform to do. So choose optimal lambda and click OK. In storage, obviously we're storing the residuals, but now we've done the BoxCox transformation, we need to, the whole analysis is now going to proceed on the transformed response. So what I need to do in order to check for equality of variance of the actual transformed response in the first place, I've got to store it. So I tell Minitab to store the BoxCox transformed response. Click OK, OK again, and there's the residuals from the previous analysis, previous video. Here's the residuals from my analysis with the transformed response, and there is the BoxCox transformed response. Okay, so up here we can see that Minitab has then BoxCox transformed the data, and the actual, the value of lambda that it chose was 0.295. Got quite a large error about it there. I mean, the confidence intervals about that lambda are quite large. So what Minitab has said is the nearest, the nearest rounded value of lambda is 0.5. And I think, don't quote me on this, I think a 0.5 lambda might be a log to the base 10 transformation. Can't remember. But anyway, we've got a transform has taken place. And there's the transform response. And there then is the analysis there. Now, if you've seen the previous video, you'll see those values are different. Look how the interaction has gone down quite a little bit there. But before I then pay any heed to this actual analysis here, what I've got to do is check if the BoxCox has worked. We want to see if we've brought that Levene's p-value up. So before I even look at the analysis, I now go and test for equal variances, not on the not on the original response, but of course on the BoxCox response goes in there. And let's see what that's done to our Levene's p-value. As you can see, look, before the Levene's p-value was 0.770, what it's done here is brought it up a little bit. Now, this analysis is pointless, really, because we had no violation to the assumptions of the analysis in the first place. As I said right at the beginning, imagine that p-value there was sort of 0.03 something, 0.04 something. We're just a whisker away from being able to being able to fail to reject the null hypothesis of Levene, but we just needed to push it up a little bit. We can see then that the BoxCox has just brought that value up a bit. So it's the transform has reduced those variances a tinsy bit. The residuals will be will be a little bit more normally distributed. So that's when we would want to use BoxCox. You can see then it was all the option to do it. The option to do the BoxCox transformation was built into the options for the general linear model. If you're wanting to BoxCox transform during a regression, then in the regression, fit the regression model, again in options, we've got this again. So we can do a BoxCox transformation of our responses or our predictors in a regression. Lots of final year projects that I've seen have had non-equal variances. Sometimes BoxCox makes a difference, sometimes it doesn't. If we're in a situation, if I was in this situation here where I had done my BoxCox response, BoxCox transformation, and this p-value was still way below 0.05, then it's not going to work. And I would sort of give up on trying to transform this data to normality. What I'd be seeing in my interval plot here, as I said before, is tiny error bars on some of these means and huge error bars on other means, just showing us that no amount of transformation to the data is going to shrink big error bars and expand small error bars. It's just not going to work. In that case, if this p-value here was still way below 0.05, then in the case of this analysis where I've got a single response variable, two predictor variables and an interaction term, then I would go to the shear array Hare test. That looks quite daunting because there's no single option to do it in Minitab. But if you go to Calvin Dytham's book, Choosing and Using Statistics, which you can get as an ebook via the Research Analytical Skills KLE page, you'll see how to do the shear array hair test in Minitab, and there's a worked example there. I would then apply that shear array hair test in this case, should this p-value still have stayed below 0.05.